Hi, I'm Mike from Hackaday, and I'm here today with Nacer Chahat, and he is from NASA's Jet Propulsion Laboratories in Pasadena. Welcome to the Supplyframe Design Lab.
Thank you for inviting me. I appreciate that.
So it's a really rare treat, I think, for me and for everyone at Hackaday because you are kind of a rare breed. You are a microwave and antenna engineer designing both communications and also doing a little work with radar on satellites.
Yeah, that's correct.
So how long have you been doing this kind of work?
So at JPL, I started 4 years ago. And before that, I was doing my PhD. So before that, for 3 years. So a total of 8 years now.
And what projects have you worked on?
So since I joined JPL, I worked on a lot of research and development projects. And also worked on Marco, which is the Mars Cube 1, which is the first CubeSat that will go to Mars. And it's going to fly alongside InSight. InSight is a lander that will land on Mars, and during the entry, descent, and landing phase, InSight will transmit the data to the CubeSat, and the CubeSat will relay that data to Earth directly.
So are there currently satellites going around Mars?
Yes, there is a large spacecraft, yes, that does that. The thing is, for this specific case, the satellite that we usually use, which is MRO, was not properly aligned. So what will happen is that InSight will transmit the data to MRO, but our MRO won't have a line of sight. So for several hours, it won't be able to transmit the data directly to Earth. So the former JPL director actually challenged us to find a solution to just relay the data directly, which is called bent pipe. Bent pipe means as you receive, you transmit directly the data to Earth with the same data rate.
So are there separate communications channels for satellite to satellite and satellite to Earth?
Yeah, that's a very good question. So the lander usually communicates at UHF with the Mars orbiter, and then the orbiter transmits to Earth at X-band or K-band, depending on the scenario. So the Mars Cube 1 won't have K-band capabilities, only X-band, so we'll use X-band to communicate to Earth.
So on this satellite that will be in orbit around Mars, what are the challenges of getting a signal from what is a relatively small piece of equipment all the way back to Earth?
Yeah, so that's a very good question, and that was the main challenge with Marco. So the antenna gain drives the distance at which you can communicate, but also the power. So we're limited in terms of power because that's such a small spacecraft. That's one thing I didn't say. CubeSat is about 30 by 10 by 20 centimeter. So it's basically the size of a shoebox to tell you how small it is. So there you have a lot of things that you need to put. We have power, we have solar arrays. There is so many things inside that you have to carry on. And then we have the radio, which needs to be much smaller than what we had before. So JPL actually developed a radio that is called Iris. This is a very small radio. It's about this size. I wish I had a model here so you can see. Very small compared to the previous one that we had. And so, as I said, they are very limited in terms of power. And there is not much we can do to increase the power. So then it all comes down to the antenna, and the antenna size is what drives how far we can talk to. And so basically, system engineer will do the math, telecom system engineer will do the math, and come back to us and tell us, hey, we need an antenna with a gain of roughly 28 to 30 dBi. We do the math very quickly, and it comes down to about an antenna that will have an aperture of 30 by 60 centimeter, if I'm correct. Yeah, about this size. So it's 3 times the face, the side of the CubeSat. So you need an antenna that is 3 times the size of the CubeSat. So you need to be very clever and deploy something that fits into such a small sat. So what we came up with, the idea that we came up with for this specific satellites, because we didn't have any available storage volume inside the CubeSat. So that makes it very complicated. You need an antenna that is 3 times the size of the satellite, but of course you don't have any storage volume. So
literally nothing, no room inside at all.
I think they gave us about that thickness.
Okay.
That's about it.
Yeah.
And so at first we were like very skeptical and wondering what we could do, and then we finally come up with having a deployable reflectarray that behaves the same way as a reflector antenna, the parabolic dish that everyone knows. In that case, this is completely flat. Mm-hmm. So we made 3 different panels that I can fold on top of each other and lay on one side of the CubeSat and deploy one after another. So on one side, you have the UHF antenna that actually received the data from the lander, from inside. That was not that easy either, and I'll show you, maybe, no, we can't hear, but that's also an antenna that lay down on one side of the CubeSat. My friend came up with that idea, and then just pop up. Okay. Just like a jack-in-the-box. Right. And on the other side, we have the high-gain antenna, which operates at X-band, and that relay the data to Earth. So inside, transmit here, and that antenna transmit back to Earth. So that's the whole idea. And here you can see the reflectarray. So there is 3 panels that fall on top of this surface of the CubeSat, and you end up with a large aperture antenna like that that allows us to communicate with Earth. So that's basically the enabling technology for such an instrument. And here what you see here is actually the feed. Mm-hmm. So that's the source that illuminates the surface. And so you see that's a rectangular face, so we had to have an array here so that we have the illumination that is more narrow on that side and wider on this side.
So do you think there's a lot of power in the future of space exploration and small vehicles like this?
Yeah, absolutely. I think that small sat are actually an opportunity to do cheap missions, and it also in a short time. So we actually did that in roughly a year.
Oh, wow.
From the beginning to the end, roughly a year, which is extremely fast for space satellites.
Oh, that's great. I can't wait to see that go up.
Me too.
So one of the other things I was really interested in is the RainCube program, which has a very unique antenna itself.
Yeah, so RainCube will be, to the best of our knowledge, the first radar in a CubeSat. This is completely different because in that case this is Earth science, so it will be on low Earth orbit, orbiting around Earth, and will actually collect a lot of scientific data, very useful. We will have a lot of information about the rain and clouds, and just out of a small satellite that is also 30 by 20 by 10 centimeter.
But you need a pretty large, relatively large parabolic dish
yes,
for this?
So in that case, this was extremely challenging because for the same reason we have a very small storage volume, but we need a large aperture. And even more complex is that now we're operating at Ka band because that's the frequency that the scientists were interested in. And so the reason why at Ka band is much harder, it's because you need a good surface accuracy. Mm-hmm. So the surface accuracy that we need to achieve for this reflector surface is within plus minus 0.25 millimeter. So that's extremely challenging. Mm-hmm. And so for the first time, we're using a mesh that is much denser. They are usually defined in terms of opening per inch. And so in the past, I think most missions are using 10 to 20 OPI, opening per inch. And in that case, we're using a mesh that is 40 OPI, so it's much denser, and that's why we're able to use that at Ka band. So there is a lot of challenges that we had to overcome, RF-wise and also mechanically. And so we worked very tightly between the mechanical engineers and the RF engineers. That's one thing that I really want to insist on, because if the RF engineer were trying to deliver an antenna by their own, they will not be capable for such a challenging project. If the mechanical engineer were trying to deliver an antenna by their own, that will also be extremely challenging. So that's why working very closely together allow us to come up with the most efficient antenna design, and actually we come up with a design that had an efficiency of 56%. I could just say 55%, but we're very proud of this 1%, so I insist on the 56%. And really, the reason why we have been able to do that is because we work so tightly together. For this project, we have some volume. We had 10 by 10 by 15 centimeter, but we needed to have an antenna gain of 42.5 dBi, which turns into an antenna aperture of 0.5 meter.
Ooh, okay.
So 10 by 10 by 15 centimeter to come up into a 0.5 meter antenna. This is very, very challenging.
So did you start with these two limitations right away? Did you know?
Yes. So right away we knew that we needed a 0.5 meter antenna. So there is nothing you can do against that. That's just the physics. The aperture antenna gives you an antenna directivity. And the antenna directivity gives you the footprint on Earth. And that's what, for radar, we're interested in.
Okay. And then you also knew exactly how much space you had to start off with.
Yes.
Okay.
Yes. Right away they tell us you have 10 by 10 by 15 centimeter, not 1 centimeter more.
So do you start with material? Do you start with folding design? Where do you even attack
So
that problem?
again, I'm not the mechanical engineer, so I won't take credit for that part of the work at all. And they have done such an amazing work. And so the way they have been approaching that is, first, they asked me to come up with an antenna design that will meet the requirement. So I tell them, hey, the ideal design I would like looks like this. And then they look at it and like, oh yeah, well, we won't be able to do it because of that reason and that reason. So basically, you have a canister of a height of 15 centimeter. And then you want to pop up a sub-reflector that will be between 0.6 to 0.8 meter, something like that. So there is a challenge because you want to limit the number of deployments. So we work together to come up with the best antenna design that will limit the number of deployments. If you limit the number of deployments, you just make it easier and the risk of failure is smaller. And that's always what we care about. We always want to get 100% of success rates. So we always try to simplify things as much as possible. So we actually come up with a Cassegrain design, which puts the sub-reflector below the focal point of the reflector. So then we are able to deploy this at a shorter distance from the vertex of the reflector.
So if it's below the point for the ellipse, how does it lose efficiency? Or?
No, it does not, actually. It does not. If you design everything properly, you can come up with a very efficient design. So another thing also is that to get this to get this parabolic shape, you need a certain amount of ribs.
Yeah.
And between each ribs, that's actually a flat surface. So you're not a perfectly parabolic shape. And so from that, when we did the math, we knew that we were limited in terms of number of ribs. The mechanical guys told us, hey guys, we cannot have more ribs, more than 30 ribs. And we're like, oh, that's going to be a problem because now we don't have we're very far from a perfect parabolic shape, especially at K-band. And so we actually came up with a solution to actually correct for this surface aberration. So when you have such a surface aberration, what happens is that the focal point of the reflector is not at the same position anymore. And so you can re-optimize this position by working on the sub-reflector, and then you can get the gain back that you lost and increase the efficiency of the antenna. As we have been talking to, there was the RainCube antenna and the Marco antenna. The RainCube antenna operates at K-band and 0.5 meter. The Marco antenna, which is a 20 by 60 centimeter antenna, operating at X-band. And now we're pushing the limits even more. We have been asked to come up with an antenna design that will also fit into a 6U CubeSat that will be about 15 times the size of one face of the CubeSat. Now, I explain you how much challenging it was already to develop this antenna, and now we need to come up with an antenna design that will be about 1 meter large.
Okay, which is
so 1 by 1 meter.
Okay. And
1 meter square.
Have you accomplished that already?
So we are working into that. This is still in development. We actually just designed a fixed model, so without all the deployment features, just to demonstrate that the RF design was properly designed. And we just went to the range, the antenna range. I just got back all the result, and so far it's very successful. So now we are starting building the deployable one. So we need to build all the different panels. We have one very bright mechanical engineer working on customized hinges, because now we want to make all of these panels to pack very tightly to make things even more compact. So for Marco, we already come up with customized hinges. For this one, they will be even more innovative. So very excited about that. We also have a feed that we'll have to deploy even farther. So about 0.7 meter away from the vertex of the reflector. And this is a reflectarray that operates at K-band, so it's even more complicated. Now the deployment of each panels need to be much better. We are talking about an angular deployment accuracy coming from these hinges of about 0.03 degree.
So is there any feedback to see if it's at the right angle, or is this all just in the mechanical design of the hinge?
Yeah, that's all in the mechanical of the hinge. And there is also more to that. We also need to, the panel flatness, we need to be very careful with that, over thermal. So that's what makes it even more complicated. So there is a lot of challenges. It's very easy, I mean, I should not say easy, but it's much easier to design an antenna on Earth than an antenna that goes to space, because there is radiation effect, thermal effect, there is multipaction also that happens in a vacuum. So there is so many challenges that we need to overcome.
Well, and it's an incredibly hard problem because it then gets compounded by the deployable nature of it. And when I think about deployment failures, there's a couple that come to mind. I think the International Space Station had a foldable solar panel that got snagged, didn't deploy well, and I think the Galileo probe had a problem.
So Galileo was, I believe, to the best of my knowledge, the first mesh deployable reflector antenna. If you look at it from very far away, it's very similar to what we did on RainCube, except that on RainCube it's double folded. So each ribs double fold, and so it was much easier.
So maybe you don't know, this is maybe a mechanical question, but how do you approach failure testing?
So we go through a lot of environmental testing. So we have, that's other challenges that we need to take into account when we're designing antennas. So we have sine and random vibe that we need to go through. There is thermal cycling. I think that's about it.
And do you often get thrown back to the drawing board from
those
tests?
I've heard stories of some of my colleagues. They would put their antenna into vibe and boom, something breaks. So even though we have very competent structural engineer, sometimes there is unexpected things that happen. So that's why we go through analysis and then test. And if we pass the analysis, we still do the test. And then if we pass the test, everything is fine. If there is a failure, we need to figure out what happened and then go back and improve the design structurally and still make sure that the antenna will perform appropriately.
I think it's really interesting to hear about what you do, but how you got here is a great story as well. So when did you figure out, like, I want to build antennas, I want to study microwave communications?
Yeah, that's a very, very good question. People are usually surprised. They always ask me, all my friends ask me, why antennas? Why? Because people just see an antenna as what you have on the TV, or we used to have on the TV. But when you go very deep to that level, you realize that it's much more complicated than that, especially when you do space applications. So the reason why I got into that is because when I was in master degree, the first year in France, it's basically very general. And at that point, I wanted to do computer engineering. I wanted to be a software engineer. And then I met this professor who was an antenna engineer, was a great researcher, has a PhD, and he wrote tons of papers, was very renowned. He was so happy. He was just so excited all the time, very happy. And I was just wondering, how come this guy, he's so happy? And then whenever he would tell us about antennas, he was so excited. So one day I told him, hey, you know what? I want to be I want to be like you. I want to be excited about what I do when I work, and I want to love what I do. So is it possible to do an internship with you? So I did an internship with him, and I just fall in love with the field. And yeah, that's what happened. It's one person that just made me get into it.
So it was actually in your graduate study is when you decided to go on in, and that's great. What university did you do your studies at?
University of Rennes.
Okay. And so to me that sounds like it's kind of late to get into it. Did you already have a background in amateur radio or building electronics as a child or anything like this?
No, actually when I was a child, I was not that interested into engineering. All I was doing was playing soccer with my friends. I was very good with math. I've always been very good with math, so I guess that's why at some point I got interested in engineering. I think the first time I decided that I wanted to be an engineer when I was about 14 years old. So when the teacher will ask us at the beginning of the year, what do you want to do? I usually wrote soccer player, professional soccer player, or engineer. But I was computer engineer, never microwave engineer or telecommunication engineer, none of that.
And so when did you realize that computer engineering wasn't your passion and you were looking at more into hardware? So
even as a microwave engineer, I still do a little bit of software engineering. Sure. So it turns out to be useful that I was curious about it. But it wasn't something that I wanted to do full time. Mm-hmm. And when I was doing it, I just didn't feel the passion about it. A lot of my friends are software engineers, and I can tell they feel the same way I feel about antenna. Mm-hmm. So I think it's just the way you feel about it. You always need to be excited about it. As soon as you find the field you are excited about it, you're going to be very happy.
Yeah, I like that. I think that's really good advice, just kind of keeping your eyes open for what is the most interesting avenue available. Yeah, that's really wonderful. Well, I got to say, this has been so great talking to you today. Thank you so much, and good luck getting your hardware into orbit around Mars. I actually have a CDR tomorrow, which is the point where we review whether or not you're ready to deliver a hardware for a flight project. So I'm very excited.